Chem 106, Chapter 16, Acid, Base, and Solubility Equilibria, Lecture 2. We can talk about equilibrium constants for acids and bases that are weak. Now, you got to remember the definitions for strong and weak. What we're referring to is dissociation, not dissolving, because all kinds of things dissolve in water. But when we talk about them dissociating or breaking apart when they dissolve in water, if they completely, or at least very nearly completely, dissociate, then that is said to be a strong solute, strong electrolyte, if you will. But if they only dissociate slightly, partially, usually 5% or less, honestly, then we call them weak. And of course, if it is strong, there is no equilibrium because, it proceeds all the way to the right. However, if it's only partially dissociating, that sets up an equilibrium and is very much more important for this chapter. Just remember, strong will not stop at an equilibrium point. It must go all the way to completion on the right. Weak, however, has to have a position of equilibrium. So when we look at this, if we have a weak acid equation, which I've written here in B1A, if you see this as a generalized weak acid equation dissociating in water, the expression we can get from this ignores the water because it's liquid, but puts the other species products over reactants in an expression that we call Ka. We can likewise do this for weak bases, where we have a generalized equation for a base dissociating in water and showing the products over the reactants ignoring water because it's liquid, and we get a Kb. The biggest feature here, and I really need for you guys to pay attention to this, that when you write an equation for any reaction that we do here in the class, for this weak acid, weak base topic anyway, if your equation generates hydronium as a product, you must use a Ka expression and a value. Because we're going to talk about these values in a bit, these Kas and Kbs. But if you generate hydronium as a product, you must have Ka. If your equation generates hydroxide as a product, you must have a Kb. Very important, and hopefully that will make sense. But I just cannot emphasize enough here. If you generate hydronium as a product, you must use Ka. If you generate hydroxide as a product, you must use Kb. Alright, so important ideas for this then is that, a large value of K indicates that ionization products are strongly favored. Small value of K indicates that reactants are favored, just like we talked about in the previous chapter. And here, the weaker the acid, the stronger is going to be its conjugate base. And so this is in terms of ionization strength. This is yet another concept that's going to become incredibly critically important in organic chemistry. Because you're going to do a lot of pK work, especially in the beginning of organic chemistry, to see how reactions proceed. And knowledge of weaker the acid, the stronger the conjugate base, and vice versa, is going to be very important. So understand this concept, that the weaker the acid, the stronger it will be its conjugate base in terms of accepting and donating hydrogen ions. All right. Now for polyprotic acids, remember polyprotic having 2 or more acidic hydrogens, these ionize in a series of steps. So you're going to lose the first hydrogen ion to generate its conjugate base, but now because that conjugate base still has another acidic hydrogen, it can undergo an ionization step in water or another base to become another conjugate base. So you'll have multiple conjugate bases in polyprotic acid titrations and such. Now, we're not going to focus on this in this course, but I want you to just have seen it. So there are a couple of sections of this outline that deal with polyprotic systems, but we're not going to do calculations on them. I just want you to have seen the information related to systems that are more complicated that have 2 or more hydrogen ions available to donate. And the reason we can kind of ignore that is because really the first hydrogen ion lost is going to be the biggest contributor. The Ka value for each successive step, so let's say if it's 2 acidic hydrogens, the Ka for the first removal is going to be very large. The Ka for the second removal is going to be very small, and by most calculations, even negligible. It will not affect your calculations, in any real way for the successive removals of the other hydrogens. In other words, those other hydrogens are going to only ionize to an extremely small extent, and so from a significant digits point of view, adds nothing to the calculation. But again, if you go on and take quantitative analysis as a second and a half year chemistry student, you take that between organic and physical, you would take quantitative analysis. Then you'll talk a little more in detail about polyprotic acid base calculations. But honestly, like I said, for here especially, having more than one acidic hydrogen is negligible because only the first ionization value, the first Ka, has any meaningful number as far as significant digits go. Aqueous solutions of salts. Now, salts can fall into 3 categories. A lot of salts are neutral, like sodium chloride. If you put it into water, it does nothing to the pH because sodium chloride does not hydrolyze in water. And so we can say that that's neutral. But certain salts will hydrolyze in water to form hydronium as a product, and so they're going to affect the pH by becoming more acidic. Certain other kinds of salts, when put into water, will generate hydroxide, and therefore those will increase the pH. All right, and so here are these following ideas. I don't want to dwell on these, but I want you to know that some salts are neutral, but certain other salts will affect the pH, and we especially those conjugate acid, conjugate base salts, we're going to focus a lot on in context down below. But for number 2 here, you can just read this and ask me any questions you have about it when you read it if there's anything you don't understand or understand when we talk about certain parts of this later on. But I'll just leave this for you to review. So going on to F, logarithmic scale relative acid strength for pKa then. So just like we can do for hydronium concentration and all, we can take the Ka values, take the negative log, and end up with a pKa value. And again, for organic chemistry, a solid knowledge and understanding of pKa will be essential. Because in the beginning of organic, when we talk about all this as review and the beginnings of how organic reactions happen, you are really going to have to understand what it means when you are given a pKa value, and especially when you look at it as a trend for stronger versus weaker acid strength. It's going to be very, very important. So you really want to get the hang of this if you're going to take organic at least in the near future. All right. So again, Ka, just take the negative log, you have pKa. And so if we go back to our old standby, Kw, then, with hydronium hydroxide and all, what we can say then is because Ka is related to hydronium, Kb is related to hydroxide, we can substitute these into that equation, take the place of hydronium and take the place of hydroxide, so that Kw equals Ka times Kb, which still equals, of course, because Kw for us at 25 degrees is always 1 times 10 to the minus 14th. Then we can take the negative log through the entire equation, and that gives us another one you have to memorize, because these two you need to commit to memory just like the others, because you can't have them at least written down going into an exam. You just have to have them in your brain. So taking the negative log all the way through gives you pKw equals pKa plus, remember these were multiplied, so this becomes plus pKb, and that value is 14. So again, kW equals Ka times Kb, and that's going to be 1 times 10 to the minus 14th. So taking the negative log all the way through gives you pKw equals pKa plus pKb equals 14. And we can do calculations surrounding that. And just having a look, yeah, we will do that as a lecture problem. All right. Another part of this that we're going to do, actually, why don't we do a few of the lecture problems first, just to get caught up on pH and pKa and all. So let's turn our attention to the lecture problems. All right. Now, remember at the beginning of this lecture, we talked about strong versus weak. In strong, there can be no equilibrium, but with weak, there must be a position of equilibrium. So if we look at lecture problem number 5, it says a solution is prepared by diluting 0.063 moles of nitric acid, HNO3, with water to a volume of 8.21 liters, and it asks what is the pH of the solution. So, forgot to change my pen color back. Sorry. All right. HNO3, we're going to have 0.0, oops, not 2 zeros, 0.063 moles into 8.21 liters of solution, right? So we can calculate molarity, because remember, molarity is moles over liters. And that's going to give us a value of 0.00767 3569 molar. All right. Now, because this is a strong, it's completely dissociated into H plus and NO3 minus. But now again, remember, there's no such thing as an H plus floating around. That dissociates in water. So you have the HNO3 going to, or sorry, just to show this properly, plus H2O, that's a plus. Notice that it's only a right-facing arrow, gives us H3O plus NO3 minus. So there is no equilibrium in this. This all dissociates into one H plus and one nitrate. So this molarity represents each of these. So H3O plus, now that we've calculated, is 0.0076735. My apologies again. 3569 molar. And the question was, what is the pH? Well, since we now know the hydronium, we can directly get the pH by taking the negative log 0.007673569, and that's going to give us a raw answer of 2.11500 26077. So as long as you got something close to that, that's all good, right? But now again, we need to round this to significant digits, the proper number of significant digits. And when we do, analyze it through properly, and what you can see is we had 2 significant digits here, 3 significant digits here. So this division, you're going to have 2 significant digits, which takes you over to here, and that gives you 4 decimal places. Not that that matters. We're still on 2 significant digits. But then we're going to take the log of that 2 significant digits. When you take the log of 2 significant digits, that means you must have 2 decimal places. So when we cut this, then we go after 2 decimal places. The 5 turns that 1 into a 2. So our final answer here is 2.1. I don't know why my pen is acting up. My apologies for that. The pen is definitely acting up today. But it's 2.12. And that's the answer for this problem. Number 5 then. What is the pH of this solution? Because there is no equilibrium, I can't emphasize this enough, that this proceeds all the way to the right. You can simply take that hydronium value and calculate the pH directly. But what if, number 6, you have a solution of a weak acid? We can't do the same thing because we don't know how much of the acid is dissociated in the solution to make hydronium. Because remember, weak acids are only partially dissociated and very weakly dissociated at that. And so we don't know how much H3O plus there is in order to be able to do the pH directly. We have to do some calculation when it's weak. So look at number 6. A solution is prepared by diluting 0.063 moles of acetic acid with water to a volume of 8.21 liters. I did this on purpose so you can see how a weak acid compares to a strong acid when we dissolve the same amounts in the same volumes. And it asks again, what's the pH of the solution? But notice this time I gave an extra piece of information. You need to know the Ka for this because it is an equilibrium situation. You know, because we're going to have the... I can't believe I didn't change pen again. All right. You're going to have the HC2H3O2 aqueous plus H2O liquid. But this time, because it's weak, it must go into equilibrium. And that's going to give us the C2H3O2 minus aqueous plus H3O plus aqueous. And you should get good at writing these equations out. You know, I didn't give it to you in the problem, but you should be able to write it out as the dissociation of that substance in water to give you those products. Notice we generated hydronium as a product. So what kind of K expression do we need? We need a Ka. But we'll come back to that, because right now what we need to do is figure out, just like in the problem before, the molarity of this. And when we do, we see that the molarity, just like in lecture problem 5, the 0.063 moles of acetic acid dissolved into 8.21 liters of solution gives us a molarity of 0.007673569 molar. I don't need to repeat that calculation. You've already seen it just a minute ago in the other calculation. So we know that's the initial concentration of the acetic acid itself, this species. And because there is equilibrium, don't you think we need an ice table to help us through this? Good, because we do. All right, so that means then that the 0.007673569 is the initial acetic acid concentration. The water is liquid, so it can't be used anyway. So you just put a big X through that whole column. Now, because we're putting the acetic acid into pure water, the initial concentration, by logic, right? By logic, what is the initial concentration of acetate? If it was pure water to begin with and we put acetic acid into it, initially there had to be 0 of this. And how much hydronium existed? Yeah, we know there's 1 times 10 to the minus 7th originally, but it's so small that we just count it as 0 because all we're interested in is the hydronium generated from this anyway, from this acetic acid dissolution. So we say it's 0. So we have the initial concentration of the acetic acid, the acetate, and the hydronium. So now what we need to figure out is the change. Now that's the kind of the conundrum here. We don't know how much dissociated. We don't know yet. We need to do a calculation. So when we don't know, we always say minus X for the change in concentration of a reactant. And since these molar coefficients are all 1 to 1 to 1, this must be plus X for acetate and plus X for hydronium. So on the change line, I'm sorry, that's the change line. The E line, you're going to have the 0.007673569 minus X, X, and X on the E line. Now, we can write a K expression. And again, you see we generated hydronium, so you know this is going to be a Ka expression, and that's going to equal C2H3O2 minus times H3O plus all over HC2H3O2. All right, and that was equal to 1.8 times 10 to the minus fifth, because I gave you the Ka in the problem, 1.8 times 10 to the minus fifth. Now we can plug that in, and we can see that we have X times X in the numerator, because each of the acetate and hydronium is X. And for the acid, we have 0.007673569 minus X. Wow, this looks like it's getting set up for a quadratic, doesn't it? But, new rule. If I take the absolute difference between the initial concentration and the Ka, if those two values differ by an absolute 10 to the 2 difference, then this minus X becomes negligible. What I mean is, convert this into scientific notation. So I'm going to use this color again here. This is really 7.673569 times 10 to the minus 3. It's this 10 to the minus 3 and this 10 to the minus fifth that I'm interested in. So 10 to the minus fifth minus 10 to the minus 3 is the same thing as saying 10 to the minus fifth minus 3. And what I want is the absolute difference, so take the absolute of it. That becomes 10 to the minus fifth plus 3 equals 10 to the minus 2. And again, that's 10 to the 2 difference. That meets my threshold of being able to ignore the minus X. All again, this might look strange at first, but it's deceptively easy, and it saves you from having to do quadratic. Because by all means, if you want to do the quadratic, there is nothing stopping you here from setting this up and doing a quadratic for it. But if you want to save a little bit of work, you do this test. The initial concentration value that you have, put it in exponential notation if it's not already, and compare that exponent to the exponent of the Ka value, or Kb, depending on what you're solving, but the K value nonetheless. And notice we have 10 to the minus fifth for the K and 10 to the minus third for the initial concentration. So if I set this up 10 to the minus fifth minus 10 to the minus third, that's 10 to the minus 5 minus 3 minus a minus 3. But we take the absolute value, I end up overall just barely meeting the criteria if there's an absolute 10 to the 2 or greater difference between the initial concentration and the K value. That means we can ignore this. All right, so now I've filled up this page. I'm gonna add a new page here then. And so going back to what I have then, I had the 1.8 times 10 to the minus fifth equals X times X over the 0.007673569. But now I can get rid of that minus X because it's negligible. And now I don't even have to worry about a quadratic, because I'm going to have the X squared over that 0.007673569. And so 1.8 times 10 to the minus fifth times 0.007673569 equals X squared. And looking at my notes, when I do this, I have Unfortunately, I did not calculate that. My apologies, but you can. And then we take the square root of it. So I'm just going to skip to the chase here. That in my notes, I already have the x value, because you multiply these two together and take the square root to get x. You know that. You're going to get 3.716506989 times 10 to the minus fourth. And again, because x is the same thing as hydronium, if you go back and look here, that when we solve, how the x is the same thing as equal to the hydronium. So, switching back, this equals the hydronium concentration. And the reason that's important is because we're trying to calculate the pH. So now we know the hydronium ion concentration in solution. So the pH is equal to the negative log of 3.716506989 times 10 to the minus fourth. And that's going to give me a raw number which I apologize, I did not write that down either, that is going to then round. And now again, because we had two significant digits just like we did in the previous one, and now we're applying a log to it, that means, two significant digits applying a log, then I need two decimal places. And so the final answer out of this, and I apologize for not having the raws on there, but you can calculate this and be sure, I end up with a pH of 3.43 as a rounded answer. So make sure that you have that as well. And what I want to make a point is between lecture problems 5 and 6, even though we used monoprotic acids for both, nitric acid in 5 and acetic acid in 6, you can see the real difference here that with the strong acid that had no equilibrium, it just completely dissociated. That gave us a pH of 2.12. But with 6, the acetic acid, even though it's the same amount in the same amount of solution, this dissociation was very limited, and that changed the pH, and its value is 3.43. And in the logarithmic scale, the difference between 2.12 and 3.43 is actually very large. Though, because it is a logarithmic scale, the difference between 2.12 and 3.43 is very large. And so you can see that weak acids, because of their limited dissociation, have much higher pH values relatively for acids. All right. Hopefully this makes sense. But the thing is if I ask you to calculate the pH of a strong, then you just calculate it directly once you have the molarity and such. But if it's weak, you must go through all the equilibria stuff that we've done here. You must build your ice table and use the K value given to you. Although that's another interesting thing. In this, you notice I gave you a Ka. And that is what you needed because you generated hydronium in solution. What if I had given you a Kb instead in there? Hopefully you would know better than to plug that in because generate hydronium, you need Ka. Had I given you a Kb in the problem, you could have used what you know on the equation to convert it from Kb to Ka, correct? How would you do that? If you were given Kb but desire Ka, since you already know that Kw equals Ka times Kb, then to get Ka, you would take Ka equals Kw divided by Kb. And that's 1 times 10 to the minus 14th, over whatever Kb value you had. And then that would give you the Ka that you could use in the problem. So you can do the switch. You can use the arithmetic on these equations. This is why you have to have them committed to memory, is so that situationally you can convert whatever's given that's not useful to something that is useful. All right. Okay. All right. Just want to be sure where we're at. Let's go back to the lecture outline then. And we understand these equations now with pKa. Oh, no, I apologize. We got one more lecture problem. My apologies. Number 7. Because we already understand pKa now and pKb. So look at number 7. It says that ammonia has a pKb value of 9.25. So for NH3, pKb, I'm making a mess of this. Hold on. The pKb is 9.25. And again, because this all revolves around the Kw and pKw, then we can calculate pKa. And because we know that pKw equals pKa plus pKb must equal 14, we can take then, to get pKa, that must be the 14 minus pKb, and that's 14 minus 9.25, and that's going to be equal to then 4.75. Hopefully that makes sense, and see how easy that is. These should just be give me points then. This shouldn't require any real effort to do a conversion directly between those two entities or between Ka and Kb using Kw again. Everything revolves around that value of Kw. All right, now we can go back to the outline. All right. Types of acid-base reactions. We can have several situations. We can have strong acid, strong base, in which case, again, it goes to completion. There is no equilibrium. It must be driven all the way forward. We can have the reaction of a weak acid with a strong base or a strong acid with a weak base. And now we have to do some calculations. And this is what we're going to play with. This part is the interesting part that's going to be fair game for this course, and I'll show you this by a lecture problem in a few minutes how we do this. But essentially we can mix equal molar amounts of either strong base or strong acid with a weak acid or weak base respectively, and we can do a calculation then called a slingshot to solve that kind of problem, because it involves two steps. Since there is a strong involved, there is no equilibrium, but there's also a weak involved, which means it hydrolyzes in water, which must establish an equilibrium. That's why we call it a slingshot. It's going to go all the way forward, then partially the way back on the equilibrium. But like I said, I'm going to show this to you via lecture problem in a few minutes. But I just want to point out that you have these 4 situations. You can react strong with strong, weak acid, strong base, strong acid, weak base, or we could mix weak acid with a weak base. And again, you can do the calculations based on that. But these middle two, B and C, are where we're going to focus most of our attention for that kind of calculation. But we can just do general calculations with equilibrium constants also. And so again, just like in chapter 15, we can use initial information and a K, such as the initial information being, say, a pH, which we can convert to hydronium then, right? And then we can use K and all of the stuff surrounding Ka, Kb, pKa, pKb, all that stuff to solve accordingly. You have the tools now using an ice table to solve. And then, like I said, we can also do a slingshot. And so let's look at lecture problems. Let's see where we're at for these lecture problems. Yeah, we are ready for the slingshot. Number 8. So let's again, we're going to be able to calculate. Let's switch over. All right. Number 8, what is the pH of a solution that results from mixing 65 milliliters of 0.2 molar sodium hydrogen carbonate solution with 65 milliliters of 0.2 molar sodium hydroxide solution at 25 degrees C? The Ka of bicarbonate is 5.6 times 10 to the minus 11. All right, that's plenty of information to work with. But now, you should know that all group 1 and group 2 metal hydroxides are strong bases. So just in case you had any question about what is strong and what is weak for bases, because, and let's say it again, strong base, group 1 and group 2 metal hydroxides are all strong bases. Pretty much everything else you can take to be a weak base. If it's not a group 1 or group 2 metal hydroxide, it's weak. But you should also have memorized the acids that are strong and the acids that are weak. And, just a clue for this course now, if an acid has carbon in it, any carbon, it is automatically weak. There are no strong acids that have carbon. So if carbon is part of the formula, it's automatically a weak acid. But as far as bases go, group 1, group 2 metal hydroxides are all strong. Everything else, especially ammonia or any other nitrogen-containing one, are all weak bases. So let's look at this then from an equation point of view. We're going to mix 65 milliliters of 0.2 molar sodium hydrogen carbonate. But now again, we are to the point, we're sophisticated enough that we can write ionic, the net ionic equations. So the sodiums are always going to be spectators for this. They're just along for solubility reasons. So in reality, all I really care about is the fact that I have bicarbonate in solution that I'm going to react with, and it's sodium hydroxide. So again, get rid of the sodium. It's just a spectator. So it's really hydroxide that I'm interested in. And because hydroxide is a strong base because it was attached to sodium as a group 1 metal hydroxide, therefore it's strong, there's only a right-facing arrow. It must go to completion. And what that's going to generate is carbonate, which is 2 minus, and H2O, which is liquid. All right, we see how this works. Sodium hydrogen carbonate reacting with sodium hydroxide. So again, we don't care about the sodiums. Hydrogen carbonate reacts with hydroxide to produce carbonate and water. All right, so now we can look at our details here that we took 65 milliliters of 0.20 molar and 65 milliliters of 0.20 molar. Now this is important. Now the water is irrelevant over here. What's important is for the carbonate. This creates 130 milliliters of solution, doesn't it? 65 mils poured with 65 mils gives us a total of 130 mils of solution. When you double the volume, you have the concentration. Because, again, I'm just going to draw this down here to represent this. Molarity is moles per liter. Now, the number of moles of bicarbonate is not changing. Like the carbon species here, all we're doing is changing the hydrogen, but there's still the same amount of carbon species from both sides, so this doesn't change. But the volume, where it was in 65 milliliters, is now a total of 130. So, when you hold the numerator constant, but you increase the denominator, that means the value goes down. Value decreases. If you double this volume, then you half the concentration. Because now you are dividing this constant number over double the denominator, that cuts it in half. Okay? So, again, what I'm saying here is that we doubled the volume with the same concentration here for both solutions. If we doubled the concentration, then doubled the volume, I apologize, then that means the concentration, must be cut in half. Double the volume, half the concentration. And you can see that mathematically just by looking at the units of molarity. So let me erase this down here. All right. Okay. So hopefully this makes sense. Double the volume, half the concentration. And this first step, because this hydroxide came from a strong base source, it can only go to the right. So now, once we go to the right, carbonate is a weak base. It hydrolyzes in water. So what we do is we turn it around. This is the slingshot. We've gone all the way to the right with this reaction, but because carbonate is weak, it must pull back. And so just write products as reactants, reactants as products. So we rewrite this then. So we have carbonate, 2 minus aqueous, plus H2O, liquid. Now it's going to establish an equilibrium because carbonate's weak with the bicarbonate and hydroxide. Oh no, we've generated hydroxide in solution. What does that mean we need for K? Kb. Because we generated hydroxide, we need Kb. So the Kb expression from this equation is going to be the concentration of bicarbonate at equilibrium times the concentration of hydroxide at equilibrium over the initial concentration, or not initial, but the carbonate concentration at equilibrium. The original carbonate is what I was saying. So this is going to be it. But remember, the only things that can go into the K expression are E-line values. So what we need to do is an ICE table to solve this. So starting again, carbonate, aqueous, plus H2O, liquid, is going to give us an equilibrium of bicarbonate and hydroxide. All right, and this is important that it generates hydroxide and we need a Kb. But what we need to do is calculate the E-line values so we can plug them into our expression. All right, so now, again, we did, from this previous information, we found that the initial concentration of carbonate is 0.1 molar. That was the whole point of understanding double the volume, halve the concentration. Water is liquid, so again, we just X out that column. And because we're starting from this point, we went in this reaction here, we went all the way to the right. That means there was none of these left. It's all this. And so there's none of this whenever we turn this around, because now we're just starting again fresh. So the the bicarbonate and the hydroxide concentrations are 0 at the outset of this new equilibrium reaction. So now change again. Logically, we don't know yet. So minus x, and plus x because it's all 1 to 1 to 1. So on equilibrium line, we have 0.10 minus x, and x. So filling in. Oh, no, wait a minute. Look at the problem again. And it said we need, because we generated hydroxide, we need a Kb. Let me check the problem again. Be sure I had a Kb before I progress any further. Oh no, we were given a Ka. But of course you have the tools. You can convert Ka to Kb because Kw equals Ka times Kb equals 1 times 10 to the minus 14th. And so we're given Ka, but we want Kb. Kb equals Kw over Ka. 1 times 10 to the minus 14th over the Ka given, which is 5.6, and it's really 5.5555 out to infinity, times 10 to the minus 11th. That's going to give us a raw answer, not a raw answer, but a rounded answer of 1.8 is, and that's good enough because this only gives us two significant digits anyway. 1.8 times 10 to the minus 4. So that's our KB that we need now to do the rest of this calculation. All right, so again, new page. Because now we know we need a KB because that's going to be the bicarbonate times the hydroxide over the carbonate that we started with. All right. And we know that's going to be 1.8 times 10 to the minus 4th equals x times x all over 0.10 minus x. Now again, we could set up for a quadratic, but why not test it? 0.1 is 1 times 10 to the minus 1, and that's 10 to the minus 4. I think visually you can see that's a greater than 10 to the 2 difference, right? That's a 10 to the 3 difference. So, with that in mind, that means that the x here is negligible, and I don't need to worry about it. It's not going to add anything significant into the answer if I ignore it. If I ignored it and did the calculation versus if I did the quadratic, if I left it there and went through all the trouble of the quadratic, my answer is going to end up being the same significant digits anyway. So why bother? All right, so then that means we have 1 point, got to change color again. Go backwards. There we are. If we have 1.8 times 10 to the minus 4 times the 0.10 equals now the x squared from this up here, right? And so that's going to be 1.8 times 10 to the minus 5th. So then square root of both sides. X is going to be, just want to be sure I have this correctly, 4.24 264 0687 times 10 to the minus 3rd. And because, again, we're talking about things that are molarity. But wait, this is not hydronium. This is hydroxide that we have X equal to. When we go back and look at our ice table, you got to be very careful. That's hydroxide. And we're trying to calculate pH, but this is hydroxide. So now you've got a variety of ways that you can go about solving this, and it's all the same. X equals hydroxide, and so you can either use that in the KW to calculate hydronium, or you could turn this into a POH and then use the pK values and change it into pH directly. It does not matter which way you do it. Again, you can either take this hydroxide, because remember that, colors. This is equal to the hydroxide. That does not give us pH. We must have hydronium to do pH. So you could either take this, that hydronium equals Kw over hydroxide. Or we could just take and calculate, that POH equals the negative log of the OH concentration, and then pH equals 14 minus POH. Either way, you've got these two ways that you could solve this problem, and it doesn't matter which way you do it. Right? Okay. So, we're going to get the same answer regardless. So let's go ahead and go with the POH method. And what we'll do then is we had the hydroxide concentration. That was equal to 4.24 264 0687 times 10 to the minus 3 molar. All right, so POH is going to equal negative log 4.242640687 times 10 to the minus 3, and that's going to give us a value of 2.372363747. And again, close enough on calculator. If you got something slightly different, it should be at least pretty close to that, right? So now, that's our POH. pH is going to be equal to 14 minus POH. 14 minus 2.372363747 gives us a raw number of 11.62763.625. And again, when we went through all of this stuff and looking at all of our numbers, there were 2 significant digits. And so again, blah, 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 addition, not addition, subtraction, but applying logs, multiplication, division, applying logs. That means that there were 2 decimal places here. 14 is taken to be an exact number. There's no decimals to it. That's not 2 significant digits. It's not that there's no decimal places. This is an exact number, so significance is irrelevant to it. You got to remember from way back when, exact numbers, significance is infinity, and therefore not used to determine significance in other numbers. So since this number had 2 decimal places, your final answer must have 2 decimal places. That 7 turns the 2 into a 3. Your final answer should be 11.63. Okay. Any questions about it? As always, either send me email or comes visit me during office hours. I'm always available, by email, and available as much as possible in my office to discuss any questions or issues you have with this. This concludes Lecture 2.